Okay, here are the key concepts that I discussed in last class. Say, if you have a differential equation, the solution that you should assume for any differential equation is going to be something like a e to the lambda t, where a is a constant and lambda is also a constant. If you look at the differential equation for a simple spring mass system, this equation is given as, if m is the mass, k is the stiffness, the differential equation is given as mx double dot plus kx is equal to 0, where x is the dependent variable, t or time is an independent variable, and if you start taking the derivatives of x the displacement, first derivative is the velocity, second derivative is the acceleration. So we use Newton's second law of force is equal to mass times acceleration and get this equation mx double dot plus kx is equal to 0. As long as you have an equation wherein there is no force term, so this is called as no external excitation, force, and this coefficient m and k, they are constant, you can blindly assume the solution to be x of t is equal to a e to the lambda t. So x dot is going to be lambda a e to the lambda t. X double dot is going to be lambda square a e to the lambda t. You substitute these solutions in your differential equation given by 1, and you land up with lambda square m a e to the lambda t plus k x is e to the lambda t is equal to 0. And again, a lambda t gets cancelled, a lambda t gets cancelled, and you have the classic equation, which is nothing but the eigenvalue problem, which is equal to 0, and lambda is given as plus minus I square root of k by m. So lambda has two values. Lambda 1 is I square root of k over m. Lambda 2 is minus I square root of k over m. You substitute these two lambdas in the equation that you have, and x of t is going to be a1 e to the plus I square root of k by m t plus a2 e to the minus I square root of k by m t. And this is the solution of differential equation. And this differential equation comes into picture because if you solve a scalar equation, x dot is equal to a x, this equation is x dot is equal to x is equal to a. You integrate both sides, and once you integrate both sides, you are gonna get ln of x, logarithm of x, is equal to at plus c, where c is the constant of integration. Now, if I take the exponent of both sides, so I do E and I do E both sides, then I land up with an equation x of t is equal to e to the power at multiplied by e to the power c. E is a constant, e to the power c is a constant, so this is nothing but a constant a. And this expression becomes a, which is a constant, e to the power at. So please understand, this is the reason why whenever you have any differential equation, you substitute a to the lambda t, find out the values of lambda. A stands for the constant which depends upon the initial condition. Now, one thing I want you to note, that in this expression, which is equation 2, you only have one derivative, x dot. So you will land up with one constant integration. However, if you look at the first equation, which is mx double dot plus ax is equal to 0, it has two derivatives, which means you land up with two constants of integration, a1 and a2. So you need an initial condition on displacement. What is the displacement? What is the value of x when time t is equal to 0? And you need another condition on velocity. What is the velocity when time t is equal to 0? Now, all said and done, here is the most critical part. Now, I want you to understand, I'm going to look at this equation. So I'm going to look at equation 2. And the solution of equation 2 is time on x-axis and x of t on y-axis. Because time is an independent variable, x of t is a dependent variable. Now, I want you to look at the solution, which is given by equation 3. A stands for initial condition. So this, when time t is equal to 0, so you have x of t is equal to a e to the at. I'm going to substitute t is equal to 0. So whatever value of x I'm going to get, x of t is equal to 0 is nothing but a. Because e to the at, t multiplied by small a is 0. So you get at x, when time t is equal to 0, your constant is a. So this is the value of a. So you start at this point. Now I want you to understand this small a. This is very, very important. This small a is very, very important. If this small a is equal to 0, if this small a is equal to 0, do you agree with me? X of t will be nothing but capital A. You agree with me? Because if my small a is equal to 0, then no matter what happens, whatever is the value of time, my value of displacement is going to remain the same. So this is how my displacement is going to look like. This is a is equal to 0. Now this behavior is called as simply stable behavior, which is this behavior is simply stable. Simply stable. If I were to show you how this simply stable behavior looks, imagine that you have a flat plate and maybe there's a ball or there's a ball. So here, or a rock. So this is the ball. And this is flat. You basically shift or you push the ball left or right. It remains horizontal. It remains stable. It doesn't become unstable or it doesn't become simply stable. Now, if value of a is 0, imagine a case, value of a is less than 0. If value of a is less than 0, please understand x of t is going to be a e to the power at, where a will be negative. So it would be exponentially decreasing. So this guy will be decreasing. So imagine this is a less than 0. This is called as asymptotically stable. And what do I mean by that? Imagine that you have a ball in a bowl. So imagine it is like this, and you perturb or you shift that ball or a marble. At the end, it's gonna come to this rest position. So at the end, at some time, this yellow line is going to intersect the horizontal line, which means the displacement is going to be 0. Now, if value of a is greater than 0, then x of t will be a e to the power at, but please understand this would be exponentially increasing. This will be exponentially increasing. So this is a greater than 0. Now what does this mean? So which means what you have is you have this bowl which is upside down, and you have a marble or a ball on top. So you shift it, and then it never comes back to its original position. So this is called as unstable. Unstable. So your robot could be simply stable. Your robot could be unstable, or your robot could be asymptotically stable. And all these behaviors are only dependent on this coefficient, which is A. Now, imagine what do I mean by robot which is unstable. So, robot unstable means you take your robot magician, turn off the power. What happens? The arm drops down. Because of the under of action of gravity, the arm drops down. So that means that robot is basically cannot hold its position. It's no longer simply stable, but it is going down. Sometimes what you do is you are in some type of a free movement mode. So you grab the robot, press the button, and robot moves wherever you want to take it. So that is basically simply stable. And that is basically simply stable. And unstable means you basically move the robot, and robot starts vibrating wildly. So that is uncontrolled motion. So typically the robots that you see are unstable. We need to manipulate the eigenvalues or the coefficients of exponent so that the robot behaves in a stable fashion. Now, in last class, I rushed. Yeah. Okay. Now, I will give you an example. Let's assume that I have a pendulum. I have a pendulum. Now, pendulum is right here. Okay. If I shift the pendulum from its static equilibrium position, if it goes over here, do you agree with me? It will kind of go back and forth. It will kind of go back and forth, back and forth, back and forth. Now, I want you to observe three behaviors. First, let's imagine, it's extremely important, let's imagine there is no damping. There is no damping. There is no energy dissipation. Everything is in vacuum. The only thing that is acting on this pendulum is gravity. Now, if I pull this pendulum towards the left or right side, let it go, you agree with me that it will continue to oscillate back and forth, back and forth, back and forth. You agree with me? This is simple stability. What is simple stability? Simple stability means the motion is not growing, but the motion is also not diminishing. Motion is remain where it is. You agree with me? It means it is simply stable. You perturb it, you move it, and the pendulum continues to move in the same fashion. There is no growth or there is no attenuation. No growth, no attenuation. Simply stable. Everyone understood this? Now I want you to visualize one case that this pendulum is inside some type of damping medium, maybe air. What would happen? You pull the pendulum, let it go, it's going to oscillate back and forth, but the air resistance is going to dissipate the energy and finally it will come down to its equilibrium position. Do you agree with me? Which means even though it started with like a swinging motion, finally it came to rest, which is something similar to the marble in the bowl. So that is asymptotically stable. Motion is going to zero, asymptotically stable. Maybe at some time is equal to 10 seconds, 20 seconds, 30 seconds, but at some point it will be at rest. Now, what I want you to understand is imagine a case where the pendulum, instead of being down, it is upside down. As long as this pendulum is perfectly upside down, it will remain as is. It's stuck, but imagine you start balancing and this pendulum remains upside down, perfectly at 0 degrees, no changes. This is its position, but as soon as I perturb it, I tap it or I change it, you agree with me, all of a sudden I have this growth in the amplitude. So this is an unstable equilibrium, or this is unstable. So here, when damping is equal to 0, it is simply stable. When damping is positive, or there is damping, I'm going to say, it becomes asymptotically stable. And this position is unstable. So now, in the context of DuBot, if the DuBot is going to maintain its position, even after you displace it, it's going to be a simply stable behavior. Or if the DuBot continues its motion back and forth, is simply stable. If DuBot goes back to its equilibrium position, after you give up, after you turn it off, it's asymptotically stable. Or if the DuBot arm starts vibrating violently, as soon as you take away the control, then basically it becomes unstable. Everyone understood this? Now here comes the most important part. I discussed this very briefly in last class, but I want you to understand this very, very carefully. If you have an equation, x dot of t is equal to ax of t, this is a scalar equation. What do I mean by scalar equation? Scalar equation means this equation, if I want to write down in a mathematical form, I would say x dot t is equal to 2xt, or I can say minus 2xt. A is just a number. This is just a number. It's not a matrix. It's just a scalar, just one number. However, all of us saw that the solution of this equation is E, a constant A e to the at. Do you agree with me? Same A, which was the number present here. Do you agree with me? Now I want you to understand what happens if I replace this scalar equation with some type of a matrix equation. Now, what do I mean by matrix equation? I'm going to give you a trivial example. Imagine I have an equation x dot is equal to ax and y dot is equal to by. X dot is equal to ax and y dot is equal to by. This is where linear algebra meets the differential equations. So please try to understand. I can write this equation down something like this. D by dt is equal to a 0 0 b. Do you agree with me? X and y. Now, I want you to think about what I have written here very carefully. I have this matrix equation. Do you agree with me? Which means there are more than one number, two numbers. And this matrix is a square matrix. So I'm going to write this matrix something like maybe a capital M. This is a matrix. Since the solution of the scalar equation is exponent of the scalar quantity, I'm going to write this down. Exponent of scalar quantity, I can write down the solution of this equation x, y is nothing but exponent of matrix equation. So which means E, X, P, M. M. Remember, there is T multiplied by a vector. So now you need to multiply that with a vector. And the vector is going to be initial condition A1 and initial condition A2. I want you to think about what I have written over here very, very clearly. Since the solution of the scalar equation is a constant, which is the initial value, multiplied by the exponent of a number, matrix exponent is nothing but exponent of the matrix multiplied by the initial conditions A1 and A2. Why do I need two initial conditions? Because I have two variables. I have a differential equation in x and I have a differential equation in y. Can you see this is x dot, this is y dot, matrix multiplied by this. Everyone understood this? A word of caution. You may not be able to find matrix exponent in all cases. But the case that I have shown over here, finding matrix exponent is super simple. X and y is equal to EXPM. Can you see that M times T is nothing but AT 0 0 BT multiplied by A1 A2. Can you see that this is a diagonal matrix? Do you agree with me? Which means this equation can be rewritten as x, y is equal to e to the at 0 0 e to the bt multiplied by a1 a2, which means the solution is going to be x, y, a1 e to the at and B1 e to the bt. Are you with me? Now, some of you may say, what special thing did I do? I just look at the scalar equation that I have over there. I can rewrite the solution for those scalar equations using the exponent function. Now, here is the tricky part. Imagine, what is this A and B denoting? What is A and what is B? What is A and what is B for this matrix? Okay. What are the eigenvalues of this matrix M? Eigenvalue for this matrix, you would say A minus lambda, 0, 0, B minus lambda, and then you are going to find the determinant. You agree with me? Which means you would solve the equation A minus lambda, B minus lambda. So the eigenvalues are A and B. In other words, if you have a matrix which comes from the state space representation of a differential equation, you find the eigenvalues, and those eigenvalues A and B dictate the stability of the system. And that is where the linear algebra meets differential equations. So this is something that you should keep in mind. And again, you don't have to do it by hand. You can use MATLAB or you can use Python to find matrix exponential functions and use those equations to solve the problem. But again, matrix exponent can only be found out in certain cases. That again depends upon the eigenvalues. Eigenvalues need to be distinct. They should not be repeated. Otherwise, you have to use some type of other technique. That being said, I want you to understand that if you take a scalar equation, if you find the exponent of the scalar, it gives you the solution. Similarly, if you have a vector equation, exponent of a matrix can give you the equation. And that's why, if you remember in last class, we had a spring mass damper system or spring mass system. When we express the spring mass system, something like x dot d over dt in state space, we had this equation 0, 1 minus k by m 0. And please note, when you solve this, the eigenvalues of this matrix, they dictated the stability. So eigenvalues, they gave us the stability behavior. So if you have a differential equation, a linear differential equation with constant coefficients, if you write that as a state space form or the first order form, the eigenvalues give you the stability. Any questions before I begin the next part? So remember this. Next thing what I want to talk about is I want to talk about the same spring mass system. So you have the mass, you have the spring stiffness. Now, in last class, I derived the differential equation of motion using the Newton's second law. Force is equal to mass times acceleration. But please try to understand, Newton's laws are applicable only in Newtonian frames. Which means when you go on to the quantum mechanics level, or if you approach the speed of light, Newton's laws are no longer applicable. However, there is something which is called as energy principles. Understand, energy principles, they govern the fundamental universal laws. Energy can neither be created nor be destroyed. It only changes its form. So you can derive the differential equation using energy principles. What is the advantage of using energy principles to derive the differential equation? And we are going to use the energy principles to derive differential equations for robot. I tell you the reason why. If you have a very small mass, saying maybe 1 degree of freedom system, just one mass, one spring, understanding the forces, understanding its motion is very easy. Imagine if you have a very complicated structure, maybe with hundreds and thousands of masses. Drawing the free body diagram for each mass, finding out the energy, finding out the force is equal to mass times acceleration is not a trivial job. What we want to do is, I want to come up with a technique where I can look at the physical model and write a computer program that can give me the code. Energy methods, they work beautifully when you have a problem like that. What are the energy methods? So I'm going to talk about two energy methods. One is called as Hamilton technique. Hamilton technique. And second one is called Lagrangian approach. Lagrangian approach. Typically, Hamiltonian approach is used for continuous systems. It means if you are trying to solve a worm robot problem, or if you are trying to solve maybe a soft robotics problem, or if you are trying to solve a robot which has shape memory alloys. So if you have a continuous system, then typically the Hamiltonian technique is used. If you have a discrete system, means n masses, n strings, say 100 masses, 200 strings, whatever it is, we typically use Lagrangian approach. So the robots that we are going to solve, we would use Lagrangian approach. We are not going to derive the equations, but what we are going to do is, we are going to use a MATLAB code that implements this Lagrangian approach that will give us the solution of the differential equation. Now, I want you to understand the beauty of this approach. The differential equations or governing equations of motion that you are going to see in the actual robotic systems is never going to be linear. You will never get a linear equation. Most of the equations that we are going to get will be nonlinear equations. The best way to solve these nonlinear equations is using some type of trial and error or numerical approach. So what I'm going to do today is I'm going to discuss you the Hamiltonian approach. We will discuss the Lagrangian approach, and then we will go on to the MATLAB and see how do we use MATLAB to develop the differential equations of motion for a robot, solve the differential equation for the robot, and then design the controller. So in today's class, I'm going to take very simple examples, but when I come back, we will spend some more time on solving more complicated examples. So let's start with this simple problem. You have the spring system, mass system, the kinetic energy, the equation for the kinetic energy is 1/2 mv². If the displacement is x, velocity is going to be x dot. So this equation is going to be 1/2 m x dot square. Do you agree with me? The potential energy is nothing but the energy stored in spring. We are assuming the linear spring. So this is my load. This is my deflection. So energy stored in spring, since it's a linear spring, is area under the load deflection curve. So this is going to be energy is 1/2, because it's a triangular area, load times delta. Load is given as spring stiffness K multiplied by the displacement X multiplied by X. So you get 1/2 K X square. So now this is called as the potential energy. So you have kinetic energy T and you have potential energy V. Now let's assume that there is no damping. It means the energy is conserved. Energy at the start of the motion is going to remain the same at the end of the motion. So total energy, we are looking at the Hamiltonian approach. So first, Hamiltonian. So total energy is equal to potential energy plus kinetic energy. Potential energy is given as 1/2 K X square. Kinetic energy is given as 1/2 M X dot square. Do you agree with me? If you have taken or studying linear signals and systems, this total energy function is something similar to the Lyapunov function that we use in the case of stability. So total energy is remaining constant. It means this total energy is neither going to increase nor going to decrease. Since total energy is conserved, is going to remain constant, I take the derivative of total energy. What should that be? What would be the derivative of total energy if this total energy is not changing? Zero. So if I take the derivative of the total energy, this becomes big zero. And now I have d by dt of this guy 1/2 K X square plus 1/2 M X dot square. Now if I take this derivative of this guy, this becomes 1/2 K. Please note, we have to take the derivative of x square, not with respect to x, but with respect to t. T is the independent variable, but we are going to take the derivative of x square. So this is going to become 2x multiplied by the chain rule derivative of x plus 1/2 m 2x dot x double dot. Do you agree with me? And I have 0 on the left hand side. Lot of terms cancel. 1/2 cancels with 2. 1/2 cancels with 2. X dot cancels, x dot cancels. And what equation do I get? I get mx double dot plus kx is equal to 0. This is the same equation that we got from Newton's laws. You agree with me? It's the same equation that we got from Newton's law. What is the difference here? Hamiltonian is nothing but summation of potential energy and kinetic energy. When you study a controls class, you will be exposed to something called as the Lyapunov equation or Lyapunov function. That Lyapunov function is also nothing but an energy function. As long as that derivative of Lyapunov function is equal to 0, the system is simply stable. If the derivative of Lyapunov function is less than 0, which means energy is continuously decreasing, the system is going to be asymptotically stable. Okay, anyway, so once this is done, let me talk about the Lagrangian approach. This is the approach that we are going to use again and again in our class. So please pay attention. Lagrangian approach. This is a very robust approach. Same thing, you find something called as L, which is called as Lagrangian. But Lagrangian is the difference between the kinetic energy and potential energy. Minus potential energy. So what is the kinetic energy? Kinetic energy is 1/2 m x dot square. What is the potential energy? Minus 1/2 k x square. And here is the very famous Lagrangian equation that I want you to remember, because this is the equation that will be coded. So the differential equation can be found out using d by dt of partial L divided by partial x dot minus partial L divided by partial x. Now I want you to remember this equation very, very carefully. L is the Lagrangian. This Lagrangian depends upon two parameters. Lagrangian has a velocity term x dot square, and Lagrangian has a displacement term x square. So you have velocity, that is because of the kinetic energy. You have displacement, which is because of potential energy. So Lagrangian has two variables. There is x and x dot. So Lagrangian equation is L is given as full derivative d by dt, because at the end time is the only independent variable. D by dt in the parentheses partial L divided by partial x dot minus partial L by partial x. So what do I mean by partial L divided by partial x dot? What it means is you need to treat x is equal to constant, and when you are evaluating the second term, x dot will be treated as constant. This is, please note, this is the partial differential equation. Partial L divided by partial x dot, partial L divided by partial x. I'm going to work this out by hand for 2 or 3 problems. However, we are going to use a MATLAB code that will calculate all this, find the differential equation, and solve the differential equation. The only input that you need to provide is the value of kinetic energy and value of potential energy. That makes our life extremely easy, because you have a robot, you know what are the masses of the robot, what are the velocities of those masses, so you can find out the kinetic energy very easily. You know where the robot is located, so you can, what are the springs in the robot, what is the elevation of the robot, so you can find out the potential energy. So what you need to do is, once you find out kinetic energy and potential energy very accurately, your robot dynamics problem is solved. Some of you may ask me, how do we do this? Let me tell you, I have already taught you this. because x is nothing but the displacement in the inertial phase. We get that from the homogeneous transformation matrix. X dot is the velocity in the inertial phase. Once you have the displacement as part of the fourth column, first, second, and third row of the homogeneous transformation, take the derivative of that row to get the velocity. Masses and stiffnesses will be known or given to you because it's a robot. You have either a solid model or you have actually the physical robot, so you can find the masses and the stiffnesses, and then once you substitute, just type this thing in and the MATLAB script would generate the equation, solve the equation, and give you the solution. Do you agree with me? The only last part that remains, most of the time, the robots that we are going to solve, they will be unstable. What do I mean by unstable? Unstable means if you have a huge robot with an arm in the air, if you let the controller go, that arm is going to drop down because of the action of gravity. So what you need to do is then add the controller terms. Robot controllers is extremely easy, and you already know this. How do you find out the robot controller? You cannot control the robot by any other means. You only have control over the motors that are at the joint. So you come up with some type of a controller algorithm. You provide the appropriate torques at the joints so that the robot behavior is controlled. Example. Whenever you have the DoBot and you press the button and DoBot or any other DoBot is in the free arm, understand the motors are free to rotate. But as soon as you let the button go, the motors lock themselves down, which means they apply the appropriate torque that is needed so that the robot position is secured. Robot does not drive under the action of gravity. On the other hand, if you pull the power plug, the motors no longer are providing the torque and the robot drops down. Everyone understood this? Once you understand this dynamics part, adding controllers is extremely simple. What you are going to do is you are going to add the joint torques that basically control your robot from point A to point B. Okay, that being said, I'm going to work out the Lagrangian. So partial L by partial x dot. Do you agree with me? The only term is x dot over here. You take the derivative of this, this is going to be 1/2 m, and this is going to be 2 x dot minus 0. Then you are going to have partial L by partial x, which means the first term is going to be 0 and second term is going to be minus 1/2 k times 2x. So this equation becomes mx dot. This equation becomes minus kx. Do you agree with me? Substitute that equation in the Lagrangian equation, d by dt of mx dot minus kx. Solve this and you get mx double dot plus kx is equal to 0. This is the exact same equation we derived using Newton's law. This is the exact same equation we derived using Hamiltonian approach. This is the exact same equation we solved using the Lagrangian approach. Everyone understood this? Any questions? Now what I'm going to do is I'm going to take a simple example for the robot. Okay. Now imagine I have a robot, and for the sake of simplicity, let's assume that the mass of the robot is significantly less than the mass of the payload, which means for practical purposes, I'm going to assume the mass of the robot is very small and the whole mass is concentrated at the payload or at the end effector. So this looks like a pendulum. So let's assume that this is like a pendulum robot. Now, I'm going to say this is the length of the robot arm. This is the length of the robot arm. And what I want to do is, I want to find out the kinetic energy of the mass. So kinetic, and I'm going to say maybe this is theta. So if this theta is the angular displacement, theta is the angular displacement, theta dot is angular velocity. So what would be the velocity of the mass? Remember the equation V is equal to omega times R, where omega is the angular velocity, R is the radius. So this velocity is going to be theta dot L. So the kinetic energy of this pendulum is going to be 1/2 mv square, which is nothing but 1/2 m. If you replace v by theta dot L square, I get this equation 1/2 ml square theta dot square. Now I want to find out the potential energy of this pendulum. Potential energy of the pendulum is nothing but how far is this pendulum from this datum. And you can assume datum anywhere. So if you look at this height, this is going to be L cosine of theta, because this is a right angle triangle. This is a right angle triangle. The height of the pendulum bob is L cosine theta. So the potential energy is given as m times g times h. M is the mass of the pendulum, g is the gravitational acceleration, and height is L cosine of theta. Please understand, since the height is below the datum, that is negative. Why it is negative? Because we are going below the datum. If we were to go above the datum, it would be positive, but we are going below the datum. So this equation, the Lagrangian, is going to be kinetic energy is T, potential energy is V, so T minus V. T is given as 1/2 m L square theta dot square, and V is given as plus mgl cosine of theta. Do you agree with me? Now I'm going to use the Lagrangian, which is given as 0 is equal to d by dt of partial L by partial theta dot minus partial L by partial theta. So first, d by dt, when I have partial L by partial theta dot, which means my cosine theta is a constant, my theta term is a constant. So when I take the derivative of Lagrangian, I don't have to take the derivative of this term, because note, it is partial, which means theta is equal to constant. Here theta is equal to constant. So I have theta is equal to constant. And the second equation, theta dot is equal to constant. So this equation is going to be 1/2 ml square 2 theta dot minus partial L by partial theta. Theta dot is constant. So this equation is going to be minus mgl. Derivative of cosine theta is minus sine theta. So this becomes minus sine theta. Don't forget that we have to take the derivative of this guy. This 2 goes, 2 goes. Then this equation becomes ml square theta double dot. 2 minuses become plus, becomes mgl sine theta is equal to 0. So please note, cancels out and you get the classic equation theta double dot plus g over L sine theta. This is the equation of the pendulum. You can derive the exact same equation using Newton's law. Imagine you have the pendulum. Then what you have is you have the torque, which is given by the gravity. This is mg acting in the downward direction. This distance is L. So this lever arm is L sine theta. And if you look at, if you move it in this direction, so what you have is you have the inertial coordinate system, and you have to use torque is equal to I times alpha. So you have to use torque is equal to I times alpha. Now value of torque, if you look at the value of torque, curl your fingers in the direction of torque, which is going to be minus mgl sine theta, and torque is going to be I times alpha, which is theta double dot. So this equation is going to become I theta double dot plus mgl sine theta is equal to 0. I is nothing but mass moment of inertia. Mass moment of inertia. So what you have is you have mass times the radius of gyration square. So ml square theta double dot plus mgl sine theta is equal to 0. So you get the same equation theta double dot plus g by L sine theta is equal to 0. Please understand, I am not going to ask you, as a matter of fact, you can do this for very simple problems. If you have a pendulum, maybe that has hundreds of degrees of freedom, you won't be able to solve it using Newton's approach. Even Lagrangian approach is going to be very tedious. So now what I'm going to show you is how do we use MATLAB to solve these problems. So these two problems, the pendulum problem and the mass problem, they are single degree of freedom system. It means the only one parameter that is varying is the displacement. Velocity is dependent on displacement. So degrees of freedom, number of independent coordinates needed to specify the state of the system completely is 1. So now what we will do is, we will actually look at these equations. So everyone, let's make a note for the spring mass system. You have the kinetic energy as 1/2 mx dot square. Potential energy is minus 1/2 kx square. For the pendulum problem, you have the kinetic energy as 1/2 mv square, which is nothing but 1/2 ml square. Also sometimes ml is also considered as I, which is the mass moment of inertia. So you may see the kinetic energy equation written as 1/2 I theta dot square. And now we are going to go onto the MATLAB and try to solve this system. Everyone understood? Now we will go to MATLAB. Please understand, in MATLAB, we already have the code that can, once you provide that code, the kinetic energy, potential energy, that code will calculate the differential equation of motion, whether it's a linear motion or whether it's a linear equation or a non-linear equation. Please understand, sine theta is a non-linear function. Sine theta is a non-linear function. The first differential equation that you are solving, mx double dot plus kx is equal to 0, is a linear differential equation. Even though this equation looks very simple, any technique that you studied in your differential equation class won't be able to solve this problem. Why? Because this is a non-linear differential equation. So the way this equation is typically solved is when theta value is less than 17 degrees, the radian sine theta is equal to theta in radians. So sine theta radians is equal to the radian itself when this theta value is less than 17 degrees. So if the pendulum motion is very small, then this whole equation can be written as theta double dot g over L sine theta approximated as theta, and then it becomes the linear equation. That's why whenever you see those grandfather clocks, that pendulum is not oscillating in large amplitudes. Pendulum is always oscillating like very small amplitudes, and there will be stops to prevent that pendulum to vibrate or to oscillate excessively beyond 70 degrees. Because then the pendulum becomes nonlinear and amplitude and frequency relationship is no longer linear. Okay, now we are going to go to MATLAB. I'm going to share my other screen. And we are going to go on to MATLAB. Okay, what I want you to do is, I want you to open the folder that is RAR or zip. So open the folder that is RAR or zip. So first problem that I want you to look at is something called as so I want you to look at SDOF. Go to this SDOF, and then there are two important functions. One function is equations run this first ODE, and other equation is Euler-Lagrange. So first I'm gonna pull this Euler-Lagrange equation. I want you to open this this code. I did not write this code. This code was provided by MATLAB. What does this code do? This Euler-Lagrange function is a function when you supply the Lagrangian to this function, which is the difference between the kinetic energy and potential energy. This Euler-Lagrange equation applies the Euler-Lagrange code applies the Euler-Lagrange equation, and not only creates a MATLAB function, but also creates a Simulink block. So it not only creates a MATLAB function, but it also creates a Simulink block. This is very powerful. It means if you are dealing with a robot, you have carried out forward kinematics, you have carried out inverse kinematics. You know positions of all the masses. You can find out the derivatives of the positions So you can get the total kinetic energy of the robot. You know where those masses are located. You know where your datum is. So you can find out the potential energy of the robot. What you have to do is, in this MATLAB code, just provide the Lagrangian. And this code will take that Lagrangian and solve this system, give you the differential equation, whether it's linear or non-linear, solve that differential equation, and on top of it, it will give you a nice Simulink block. So if you want to use some type of a PID control, and I'll show it to you how it is super simple to develop the controller for the robot. If you want to develop a PID control, if you want to develop MPC control, if you want to develop non-linear control, grab that appropriate block from Simulink, integrate that block with the robot, then you are done. So that actually designs the controller. Okay, so I'm gonna quickly go through this code. So this is the function that is gonna require x. X stands for the Lagrangian, which is given as t minus v. Then it is going to ask you for the states. So what are the states in the Lagrangian? Then it's gonna ask you for some parameters, the dissipation terms, and maybe it will ask you if you want to generate the Simulink code as well as MATLAB code or just MATLAB code. So if you provide m as the variable, the parameter, it generates the MATLAB code. S as the parameter, it generates the Simulink block. Now, note x are the generalized coordinates. In our case, in the case of mass, it would be the displacement and velocity x and x dot. In the case of pendulum, it would be theta and theta dot. And let's walk through the code. And again, there are different examples, but what we want to do is we just want to use this code, and this code will actually find out the differential equation of motion. But please note, this is a function. This function needs to be invoked. So I want you to go here, which is equation, run this first. This example is the same example that I solved multiple times. But now, instead of deriving the equation by hand, I'm going to use MATLAB to derive the equation and to solve the equation and to give me the plots. So let's start. So you have the symbolic variable. So you have to provide the state. The first state is going to be the displacement x. Second state is going to be the derivative of displacement x dot. xd is the derivative of displacement. You need to provide the values for the gravity, values for the mass, values for the spring stiffness. You can also provide the value for the damping, but as you know that value of d is equal to 0, that d doesn't matter. So this is exactly how you set up the problem. In line number 8, can you see I'm setting up the Lagrangian? Lagrangian has two parts. The first part is the kinetic energy, which is mass multiplied by the velocity square divided by 2. So 1/2 mv square, that is the mass. Second term is nothing but the potential energy. You have the negative of the potential energy. Just refer to your notes, and do you agree with me? This is the same Lagrangian that we derived for the spring mass system. So kinetic energy was 1/2 mx dot square. The potential energy was 1/2 kx square. So that is the Lagrangian. Now, we don't have anything else. So we define the states here, x and xd's. Please note, this order should be similar to the order that you have defined for the symbolic variables. There are no generalized forces. There are no dissipating forces, which right now there are no external forces acting on the system. So I've treated everything as 0. You can also include the damping, but for the time being, D value, as you can see, D is 0, so damping is 0. And then I invoke this function, Euler-Lagrangian, and I call this function ODE2. This function takes some time to run. So I'm adding a wait time or a pause time before, so I give it some time for the code to execute. So this pause is provided so that this Euler-Lagrange function is invoked, it finds the solution and it puts the solution in this structure. Then you have the timestamp 0 to 10. Then what you do is you provide the initial condition. 0.1 is the initial displacement, and I will say 0.2 is the initial velocity. I use a MATLAB ODE function to find out the solution of the differential equation, and then I plot it. Now what I want you to do is, I want you to run this code. I want you to run this code and see what happens. Once you start running this code, it will throw an warning, because I already have the ODE block. It's a warning. The code will still run. Please note, MATLAB is busy. The code is running. And after some time, you would notice that the code runs. And you have these plots. Can you see these plots? The first plot is the plot of the displacement, because remember our initial displacement was 0.1, and second plot is nothing but the initial velocity, because please note it started at 0.2 and it's a simple harmonic motion, so it is going back and forth, back and forth. Everyone understood this? Please run this code and make sure that the code is running. Now I want you to note that it also created something called as ODE2 block.slx. So MATLAB created a Simulink block. So if you click on this, this is the Simulink block where that code is implemented. This is the Simulink block where that code is implemented. So now what you have is you have this Simulink block that you can use to generate the exact same results, and I will show you the solution. It's actually very simple, and that should be in the answers folder. If you go to ODE block SLX, yeah, because I have the same block here. So what I'm gonna do is I'm gonna delete this and then create open SLS ODE. Yeah. Okay. ODE block. I'm gonna call it ODE block 1. So just click on this, because Simulink will not let you open the block with the same name if you have the same block. And this is the exact same function implemented in the Simulink. So what you can do is you can run this function and you will get the exact same plots that you got from your MATLAB code. So remember, you are trying to work on the robot. You have done the forward and inverse kinematics. You know the kinetic energies and potential energies. Find the Lagrangian, program this in this MATLAB code, And MATLAB code will solve that problem and also will give you a Simulink block. So you will notice when I want to design a controller, what I'm gonna do is I'm just gonna grab the maybe PID block over here and provide the feedback to the PID block, and the controller input will be fed to this Simulink function, and the whole thing, your robot will be controlled. There is one more example that I want you to look at very quickly, and that example is robot. Go to Robot Dynamics and look at the simple pendulum. In simple pendulum, again you have run this first. Variables are theta and theta dot, theta and theta dot. Now I want you to notice this is the same Lagrangian that we derived, the exact same Lagrangian for the pendulum. Run this code. It will create the differential equation. It will solve the differential equation. It will generate the plot. Everyone understood this? Please work with these scripts. Next 2 weeks, we are going to have the robot operating system lectures. Then when I come back, then we are going to use this technique and actually do some type of, we'll work on different types of robots, and then we will design the controllers for different types of robots. In the meanwhile, feel free to explore RR, RPR, RP, R90R, R90R, robot dynamics. With that, I'm going to stop here.